Okay, the next thing we're going to study, and the last thing we're going to study in geology, is about the restless Earth. The fact the Earth transforms and changes itself, sometimes on a slow level, but also sometimes on a very fast level. So we're going to talk about all the different ways the surface of the Earth can change through the powers of plate tectonics, through the powers of earthquakes, through the powers of volcanoes. In order to understand how the Earth responds and changes and moves, the first thing we're going to get into is the layers of the Earth. Later on, then we'll get into the idea that that top layer, that crust layer that you're going to see, and it's actually going to be called the lithosphere, actually is broken into pieces and will move and shift. But before we talk about that, we got to know what the layers of the Earth are. Now, I have a couple movie clips that will talk about where they got the information, because as you look at the picture of the Earth on the screen, no one has dug as far down in the Earth into the mantle. The farthest anybody has really gone down is less than a mile, maybe a little bit more than a mile in some areas. The crust is also, as you'll see, that the top layer is a very thin layer that surrounds the Earth itself, surrounds the other layers. The crust is, there's areas of the crust that are thicker, so like mountainous areas, and there's areas of the crust that's very thinner, like at the base of waterways, like oceans and such. So we're going to get into what are the basic layers. So I gave you a worksheet that goes along with these slides, and on this slide, on the front, is what we call the 4-layer model of the Earth, and on the back you'll see that the Earth is broken into 5 separate layers. So I'm going to keep making reference to that worksheet so that you know where to fill that worksheet in and how to properly fill it in. On the front, like I said, it talks about the crust, it talks about the mantle, and talks about the cores. What I want you to do for those things is just, as you see them on the screen, write down details about each of those layers as we talk about them, because we're going to talk about them in great detail. On the back is when I will tell you, okay, here are the layers according to what's called the 5-layer plate tectonic model. And that's what's going to lead us into our next conversation about plate tectonics. So the back of the worksheet, which is just labeling the letters A, B, C, D, and E, I will let you know when to label those. So don't touch that back just yet. I'll explain when. So we're going to start with a 4-layer model of the Earth. The 4 layers, as you see on the picture there, are the crust, which is the top layer, the one you interact with on a regular basis, the mantle, which is a very thick layer that sits below the crust and above the cores, and then there actually, and I'll show you videos on this later on in the presentation here, is there's actually an idea that there's 2 cores. One that is made of solid iron, which is the inner core, and then another core that's made of liquid iron that surrounds the solid core, which you'll see an animation of later on in one of the videos, called the outer core. So the 4-layer model is the crust, the mantle, and the 2 cores. On the front of that worksheet, I'm going to have you give me information about each of them. And with crust, there's going to be 2 types of crust. With the mantle is actually going to get broken up into smaller sections, and that's going to help us label the back. And then there's 2 cores, the inner core and the outer core. And I have a couple of videos, but some notes that will also help you answer the core. So I know core is just one section. There's actually 2 types of cores. There's the inner core and the outer core. So the uppermost layer of the Earth, or the outermost layer, the one you interact with on a regular basis, is the crust. And as you saw in the picture on the left, the crust is the thinnest part, or thinnest layer, of all the 4 layers. So even though it's the thinnest, it's actually the one that protects. It's almost like the skin on your body. How it's such a thin layer that protects your muscles and your bones and all your organs. That thin layer helps to kind of block out all the things that could actually harm our skin and harm our vital organs and our bones. So the skin actually has a very important job. Well, the crust of the Earth is the skin of the Earth. It's thin, but at the same time protects the outer surface from volcanic activity, molten rock that comes to the surface, because inside the Earth it is extremely hot, and it will cause rocks to go from solids to liquids, and those liquids are going to be less dense. They're going to try and get themselves to the surface. So right there kind of gives us an idea of how volcanoes form. But we don't have volcanoes everywhere, and thanks to the crust and its thickness, the reason why we don't have volcanoes everywhere, or we don't pretty much have a molten lava pit that life could not survive on. So the outermost layer of the Earth is the crust. It's made of rock. There are 2 types of crust. The first is called continental crust. Now this crust means the continents. So North America, South America, Asia, Europe, Africa, Antarctica, Australia. I think I got them all. those are all the continents, and they're all made of a certain type of igneous rock. They all make up continental crust. The continental crust sits at higher elevations than this other type of crust we're going to talk about. And that's because we have water all over the earth. If all the crust was the same type of rock, mainly mostly of granite, which is the continent, if it was all the same type of rock, then water that lays on the surface would pour over the surface. So when you go to the ocean, I don't know if you ever notice it, but when you go to the ocean and you try to walk downhill, or I'm sorry, when you walk in the water, it seems like you're walking downhill. That's because you're standing at a higher elevation than the rest of the ocean floor, and as you go into the ocean itself, you're walking downhill on a slope that eventually will drop off and lead to the ocean floor basin, which is made of a different type of rock. So continental crust is made of granite, which is lower in density. It's more felsic than anything else. So it's why we call felsic granitic. And its average thickness is about 30 kilometers. Some of your mountains get to a thickness of about 100 kilometers. And I'll show you a picture of that on the next slide. The other type of crust is oceanic crust, and that's made of basalt. Basalt is a type of igneous rock. So it all goes back to the formation of the earth and all that volcanic activity trying to allow that heat and molten rock to get out onto the surface. Well, the basalt igneous rock, which is much more dense, it's a mafic rock, it's much more dense, it sank down deeper where gravity pulled on that more, so that the early earth, before oceans were even created, looked like a big Grand Canyon. You had granite that sits at a higher elevation, and you got the ocean basins that sit at such a lower elevation, made of two different types of rock. Continental crust is granitic, and oceanic crust is mafic or basaltic, however you want to call it. The thickness, since it's such a dense piece of rock, the thickness of rock at the ocean floors is about 5 to 8 kilometers, so much thinner than the continental crust, which sits at a higher elevation and is a lot more thicker. Okay, so which is more dense? The oceanic crust is more dense because it gives you the thinness. So let me show you this picture here. Oceanic crust might be thinner, but it is more dense. So as you look at the picture here, let's go red. Okay, this is continental crust at 30 kilometers. This is oceanic crust at 5 kilometers. Under here is the mantle. So this is where rock can be more molten than anything else. And when it's molten, it's going to try and work its way to the surface. Well, underwater is a very easy process, and then you've got, volcanic activity. Problem is, you got all these, well, not problem. A good thing is the fact you got all this water, these gallons of water to cool molten rock as soon as it gets to the surface. So volcanoes are cooled and hardened and turned into new rock the second it breaks through the surface there, even though it's thinner. In the continental crust, there's so much more space to have to get up to the surface that you don't see a whole lot of volcanoes happen around the continents. We will talk about the interaction of plates at some point and talk about how volcanoes do form. It's a different type of process we'll get into later on. The next layer below the crust is the mantle. The mantle is considered the largest of layers, most dense, a lot of heat, so you have molten rock and solid rock within it, and it is the area between the crust and the cores. It contains most of the Earth's mass. Now, here's where we're going to get basically into the back of that worksheet, because now I'm going to start taking the mantle and the crust and I'm going to combine them and give them different names. So for the mantle, the information, you could say the air between the crust and the core, extremely thick, contains most of the Earth's mass, and the fact that it's broken into parts. Some of the mantle is molten, liquid rock. Some of the mantle is solid rock. And that's where we're going to get the breakup into the plate tectonic model. Okay, now flip the worksheet over, and you'll notice that there are 5 letters on the back of the worksheet. A through E. Now, looking at the worksheet, E is the topmost layer, A is going to be the center of the Earth. Okay, so we're going to start at E. We're going to work backwards here. So E is the crust and what's considered the upper mantle. So if the upper mantle here, as it says on the screen here, the upper mantle is combined with the crust, the whole crust itself, and the upper mantle, which is solid rock. The two of them combined together make a layer called the lithosphere. So that is going to be letter E on that worksheet. So for letter E on that worksheet, Label that layer as the lithosphere. That is the uppermost layer of the Earth. It's a combo of the crust, the whole crust, and the upper part of the mantle that is more solid rock. When we get into plate tectonics, this is going to be the layer that moves and shifts. This is going to be the layer that's broken into pieces, and we call those pieces tectonic plates, as the slide tells you here. So that's going to move and shift. Now, what's going to cause it to move and shift is going to be the layer that's below the lithosphere, which is letter D on your chart. So the lower mantle, there's two sections to the lower mantle. Letter D of the mantle is called the asthenosphere. So this is letter D in your chart. So label the letter D as asthenosphere. The asthenosphere, as you see, there is the explanation. As the asthenosphere is a soft layer mantle, which means it's mostly molten and it's some solid rock. Because this layer is so molten and the solid rock sits on top, it allows the lithosphere, which is layer E, to move and shift. That's a good thing. Because when you have so much heat inside the Earth, you have so much pressure that builds up inside the Earth. The Earth needs to release that pressure somehow, some way. Otherwise, we're in trouble if the Earth's going to explode. Okay? Since the asthenosphere, which is layer D, actually allows for the lithosphere to move and shift, I call it a very viscous layer. It's a jello layer. It's not quite soft, but it's not quite hard. It allows that lithosphere on top to move and shift. If it was solid rock, then the lithosphere doesn't move, you get lockup, you get a buildup of pressure, and you get explosion. That would be very bad. Since the lithosphere is made of a very jello or viscous layer, just kind of like jello is. Jello is not quite solid, not quite liquid. That's why I give that same analogy. Since it allows it to move, it helps to relieve pressure, and that pressure is what we get in the sense of volcanic eruptions on the Earth, like Hawaii that had the Big Island, losing a lot of that volcanic material, a lot of mantle, a lot of asthenosphere coming up to the surface, and also earthquakes. So the volcanoes and earthquakes. That earthquake is just a relief of Earth relieving pressure. Okay, it just causes a lot of shaking, causes a lot of destruction. Why? Because that's where all of our stuff is. It's on the surface. So the asthenosphere is layer D. Layer C, the rest of it, which is solid rock that sits below the asthenosphere, that's the mesosphere. It's also up here. Okay, the mesosphere, wrong letter. Mesosphere is letter C. Okay, mesosphere is letter C on that chart, on your worksheet. So on the back of the worksheet, E was lithosphere, D was asthenosphere, C is mesosphere. You've heard the word mesosphere before. It was one of your layers of atmosphere. Meso means middle. It's the middle layer of the Earth according to the plate tectonic model. So you've got the lithosphere, then asthenosphere, then mesosphere. So let's take a look at a picture of what I'm talking about. So the crust, which includes the continental crust, oceanic crust, continental crust here, plus the upper mantle that is solid rock, that makes up the lithosphere. Underneath, the viscous layer down here, okay, the viscous layer down here, that's the asthenosphere. It doesn't help if I cross out the word. The asthenosphere is your viscous layer, your jello-like layer, that allows the lithosphere at the surface to move and shift, which is good. It helps relieve pressure. The last layer underneath is the mesosphere. Okay, the mesosphere is the solid layer of rock that sits below the asthenosphere and makes up the rest of the mantle. Now, on the next couple screens, there's a couple movies that are going to come up next that talk about the cores, the inner core and the outer core, and then I'll have some notes for you to fill in the front of that worksheet. My mistake. The notes come first. The other two layers of the layer of the Earth, and this is true for both models, whether it be four-layer model or plate tectonic 5-layer model, are the two cores, the outer core and the inner core. And the movies that you're about to see on the next two slides are going to talk about, or the rest of this movie, are going to talk about why it was considered to be two cores and not just one core. It's all got to deal with earthquake data. It's all got to deal with seismology. Seismology is what actually gives us the fact that we can't dig down to the core. There's no way we can do that. So how do we know? Seismograph data, so which means earthquake data, is actually what's going to give them the answers to that. Just to kind of finish this up and finish the worksheet up, here's your information for the core for the front of the worksheet. And then letters B and A are outer core, inner core. So outer core is letter B, inner core is letter A. So make sure on your worksheet that you label the layers and you give this information. The outer core is liquid iron. It surrounds the inner core. Inner core is solid iron. That's where gravity is coming from. It's coming from the source in the core, the center of the Earth. So enjoy the next movie clips.
In March 1980, geologists detected a series of small earthquakes here, beneath Mount St. Helens in Washington state. It was a signal that the long-dormant volcano was waking up. Finally, on the morning of May 18th, it did. Mount St. Helens erupted with a force 500 times the atomic bomb that was dropped on Hiroshima. A cloud of hot ash roared 15 miles into the atmosphere. "230 square miles of forest were wiped out. 6 million trees, enough wood to build 300,000 two-story houses." Throughout recorded history, civilization has lived with the threat of earthquakes and volcanoes. But the cause of their destructive power remained elusive, shrouded in mystery. It wasn't until our first great discovery that a picture of what was happening inside the Earth began to emerge. For centuries, most of what we knew about the Earth's interior came from mining operations like this one. It wasn't until scientists began using seismographs to study earthquakes that they gained a more accurate understanding of the inside of the Earth. When an earthquake occurred, seismographs measured the speed and intensity of seismic waves that vibrated underground. Using this method, scientists identified different layers inside the Earth, each one characterized by changes in rock density. For example, the first layer was the crust, a skin of rock covering the planet. Its depth varied from 3 to 30 miles. Below that was the mantle, with a depth of about 1,800 miles. As for what was below that, a breakthrough discovery provided the first clue. In 1906, British geologist Richard Oldham was analyzing seismograph readings caused by a large earthquake when he saw something odd. As the vibrations from the quake reverberated, they did not arrive at the center of the Earth as expected. It was as if they'd hit an obstacle. Oldham realized the obstacle must be the innermost part of the Earth, a dense mass hard enough to have deflected the seismic waves from going all the way through. Oldham had discovered the Earth's core. It was a landmark discovery because it set the stage for the work of another scientist who was about to help revolutionize our understanding of what was happening inside the Earth. With Oldham's discovery, many believed the picture of the Earth's core was complete. But in the early 1930s, Inge Lehmann wasn't so sure. Lehmann was a Danish seismologist who worked extensively in Denmark and Greenland, studying the velocity of seismic waves from earthquakes. In 1936, she was analyzing the seismic waves from an earthquake that had occurred several years earlier. Seismological stations around the world had made recordings of the same quake. By comparing their readings, Lehmann calculated that as the seismic waves had passed through the Earth's core, there was a change in their velocity, as if they had encountered another boundary of some kind. Then it occurred to her. Something was missing from the accepted structure of the Earth's interior. The Earth didn't just have one core, it had two. The core that Lehmann had found was the Earth's inner core. Today, through precise seismic measurements, we know that it's made of solid iron. Solid because gravity at the center of the Earth creates a pressure 3 million times the pressure it exerts on the surface. The core that Richard Oldham had discovered turned out to be the Earth's outer core. It's made of liquid iron and other elements, a hot churning mass that generates electric currents which in turn create the magnetic field that protects the Earth from dangerous cosmic radiation. Together, the two cores that Oldham and Lehman discovered form a massive structure over 4,000 miles in diameter, slightly larger than the planet Mars. At the center of the core, the temperature can be as high as 13,000 degrees Fahrenheit, which is 2,000 degrees hotter than the surface of the sun. To get a better understanding of what we've learned from the discovery of the Earth's two cores, I caught up with Dr. Katherine Johnson, a professor of geophysics doing field research at a mine location in Southern California. What made the Earth hot in the first place?
The Earth's original heat actually came from how the Earth formed. It formed through collisions of smaller bodies, we call them planetesimals. The collision of those bodies released huge amounts of heat that gave
Coming
the Earth
from astronomical distance.
That's right, just crashing into each other and turning all their kinetic energy into heat.
And so that heat's still here.
And that heat is still here. There's also heat that was released actually during the formation of the Earth's core. So all these bodies came together, they're rocky, they have bits of metal in them. That metal settled within the Earth to
Gravity.
Gravity, just by gravity. But the change in its gravitational energy going from near the surface of the Earth to falling to the center actually also released a lot of heat.
Why hasn't the Earth cooled off?
It hasn't cooled off because it actually cools very slowly. That seems perhaps surprising given how hot it is, but its original temperature was very, very hot, and so it takes the Earth is massive, so it takes a long time for it to cool. That's why smaller planets like Mars, even smaller planetary bodies like the Moon, have pretty much cooled off. Right.
But here on Earth, the cooling off of the planet is perhaps billions of years away, thanks to the intense heat of the core, which acts as a kind of natural furnace. What Oldham and Lehman didn't know was what else the furnace was capable of. And that's our next great discovery.